Welcome to the Depth Dive. Today we are jumping right into what is, I think, the biggest debate in AI.
Oh, for sure.
Are large language models, LLMs, a real path to AGI, or are they just a dead end, just a fancy autocomplete?
Right. And you see these two camps, don't you? One side says, just keep scaling, just more compute, and AGI will emerge.
And the other side dismisses them completely.
Exactly. They say they're just mere pattern matchers, that they're structurally incapable of any real reasoning. But our sources today suggest that's a false choice.
Okay, a fun dichotomy. I'm interested. So let's unpack this third position they're putting forward. It's built on an idea called substrate plus coordination. So what does that actually mean for how we should be looking at models like GPT-4 or Claude?
It means we should see the LLM as the essential System 1 substrate.
The substrate,
Yeah.
so the foundation.
Yeah, think of it as the vast, unconscious library of patterns. It's absolutely necessary, but it's not enough on its own.
So what's it missing?
It's missing the System 2 coordination layer. That's the part that's needed to bind all those raw patterns to, specific goals and real-world constraints.
I love the metaphor they use here. It really clarifies it. They compare it to fishing.
Right.
So the LLM is the ocean, this huge body of latent patterns. And when a model hallucinates, when it spouts that fluent but totally ungrounded nonsense, that's just an unbaited cast.
That's it, exactly. It's the maximum likelihood prior, the most generic fish you'd catch, just by casting a bare hook into the ocean.
So reliable intelligence isn't just about pulling up the most likely thing.
No, it's about baiting the hook with a specific intent and then using a net to filter the results against your constraints. The coordination layer is what calculates how much effort you need to pull the model away from that generic answer toward a specific verifiable goal.
Okay, but hang on. If real reasoning needs that strong external anchoring, doesn't that sort of prove the critic's point? That the LLM substrate itself is inherently flawed for AGI?
Not necessarily, because the source here formalizes this shift to reliable reasoning, not as some gradual improvement, but as a sharp thresholded event. They call it a phase transition.
A phase transition, like water turning to ice.
Precisely. And it's modeled by something called the Unified Contextual Control Theory, or UCCT.
So tell us about that. How does this UCCT govern that shift from just, hallucinating to actually having stable, goal-directed control?
Well, the theory says the whole system flips when its anchoring strength score crosses a certain critical threshold.
Anchoring strength. And what goes into that score?
It's basically three things working together. First, you need high effective support. Think of that as how good your bait is, how strongly your query pulls the right concept out of that ocean of patterns.
And what's pushing against that? The filter you mentioned.
Exactly. That's the representational mismatch. It's like the noise or instability in the context. You could think of it as the size of the mesh in your net filtering out things that don't fit. When the fit is good, the mismatch is low.
Okay, bait and net. And there's a third factor, something about efficiency.
Yes, the adaptive regularizer.
Hmm.
It's there to penalize using too much context or having too big of a bait budget. Real intelligence has to be efficient.
So when the bait is strong, the net is right, and the budget is optimized.
The anchoring score crosses that threshold, and you flip into stable, grounded reasoning.
This sounds an awful lot like human cognition. Our fast, unconscious System 1, the ocean, being regulated by our conscious System 2 control, the net and bait.
It's a perfect parallel, and their 4-year-old's cat example really brings it home.
Let's hear it.
So a child already has this huge pattern repository for animal features, fur, ears, tails. That's massive effective support.
Right, the ocean is already stocked.
Then a small anchoring event happens. An adult points and says, that's a cat, maybe shows a few pictures. That's a tiny budget.
And that small intervention recruits that whole vast pre-existing structure.
Instantly. Because the features of a cat align so well with what's already there, the mismatch is incredibly low. The anchoring score shoots past the threshold, and boom, the child now has a stable concept of cat.
But if you showed them, say, a pangolin, it would be much harder.
Much harder. The mismatch is way higher. It would take a much bigger budget, more context to make that jump.
So if that's the theory, how do you actually build a system that manages this? The source proposes a blueprint, right? Multi-agent collaborative intelligence, or MACI.
Yes, this is the missing coordination stack. It's how you turn raw pattern capacity into something verifiable. It starts with behavior modulation.
What's that?
You have agents in the system debating, but how strongly they hold their stance is tied to how well their arguments are anchored in evidence. If the evidence is strong, they yield. If it's weak, they keep exploring.
So the system's confidence is literally proportional to its grounding.
Then you need Socratic judging. There's a specific module for this that acts as a judge, filtering out poorly formed or ungrounded arguments before they can mess up the system's shared understanding.
And the last piece.
Persistent memory. A real transactional memory that tracks what was said and why, so the system can revise its reasoning and recover from errors.
So the big takeaway here really isn't that LMs are doomed. It's that the failures we see, the hallucinations, the inconsistencies, they're mostly just coordination failures. The system is just operating below that critical anchoring threshold.
Right. The debate shouldn't be about whether the substrate is good enough. It's an engineering problem. The priority isn't just making the ocean bigger. It's about building better fishing gear.
Better state, better verification, better coordination.
All of it.
So we'll leave you with a final thought on that. If we can successfully build that coordination layer, if we can securely bind this incredible pattern substrate to external reality, is that all it takes for AGI? Or is there still something else missing, beyond verification and metacognitive monitoring, something to think about? Welcome back to The Deep Dive. Today, we're getting into something that I think frustrates pretty much everyone who uses a personal AI agent. I'm talking about the lag. That, infuriating pause after you ask it to do something even a little bit complex.
It's a real paradox, isn't it?
Yeah.
We give these agents incredibly powerful planning abilities through large language models, but those models are, well, they're slow.
How slow are we talking?
The research we looked at puts a number on it. Just to generate a multi-step plan, using something like the GPT-4 API can take around 25 seconds.
25 seconds? I mean, in user experience terms, that's an eternity. That kills the whole experience.
It absolutely does. But what's really interesting is that the source material found a huge opportunity hidden in all this. They analyzed real-world data and found that about 30% of all requests, they're either identical or very, very similar.
30%. So a third of the time, we're basically asking the agent to resolve a problem it's already seen before.
Exactly. And that's a massive waste of resources.
Okay, so let's break that down. The standard workflow is pretty simple, right? A request comes in, the LLM makes a plan, some tools execute that plan, and you get a response.
Right.
So the obvious question is, why can't we just use caching? I mean, we've had that in computing for decades. Just save the final answer.
Because the similarity is in the task, not the final answer. And that's the key distinction. Traditional caching fails because two requests can have the same underlying steps, but completely different key details.
Ah, okay. Can you give us that travel example from the source? I think that makes it really clear.
Sure. So let's say request 1 is book a ticket from Hefei to Beijing for the day after tomorrow.
Okay.
And request 2 is book a ticket from Changsha to Shanghai for tomorrow. A simple cache would see those as, totally different strings of text.
Right, because the cities and dates are different.
Exactly. So it would trigger that slow 25-second planning process for both. But the actual plan needed is identical. Query the date, query flights, compare prices, and so on.
So the solution they came up with, this AgentReuse mechanism, it's about reusing the plan, not the final response.
Precisely. But that creates a couple of big challenges. First, how do you even tell that those two requests are similar if you can't just compare the text?
Right. How did they do it?
This is the clever part. It doesn't compare the raw text. Instead, it uses two steps. First, intent classification. It figures out what you're trying to do. Is this a book ticket task or a check weather task?
Okay, that makes sense.
Then it does parameter identification. It just pulls out those key variables, the origin, the destination, the time. It basically creates slots for them.
So it strips out the variables and then compares the skeleton of the request. It's comparing book a ticket from O2 with another book a ticket from here.
You got it. And that dramatically improves the accuracy of finding a plan it can reuse.
But that creates the second problem, right? You have this plan, which is probably just messy natural language from an LLM, and now you have to safely plug new information into it.
That's the other half of the puzzle. You can't just, find and replace words in a sentence without breaking the logic. So AgentReuse converts the LLM's plan into a clean, structured format.
Like a flowchart, almost.
Yeah, that's a good way to think about it. For each step, it defines the description, the inputs it needs, and, this is crucial, the dependencies between steps.
So the system knows exactly where Shanghai needs to go and that it has to happen before the price comparison step.
Exactly. It makes the parameter replacement safe and reliable.
So let's talk about the results, because when I saw the numbers, they were pretty staggering.
They really are. In their experiments on a real-world data set, AgentReuse cut down latency by 93.12%.
93%. That 25-second wait just vanishes.
It pretty much does.
Yeah.
And that's because it works so well. They hit a 93% effective plan reuse rate. Their method for spotting similarities was just incredibly accurate.
I mean, that's a game changer. But there's always a cost. What's the overhead for running all this extra classification and structuring?
That's what's so compelling. The cost is tiny. It adds about 100 megabytes of extra VRAM and less than 10 milliseconds of latency to each request.
So a 10 millisecond cost to save 25 seconds.
It's an easy trade-off to make. It more than pays for itself.
So we've cracked the code for speeding up single, simple tasks like booking a flight. But the sources hinted that this is just the beginning. There's a bigger challenge on the horizon.
There is. All of this work is focused on single intent requests. The real next frontier for making agents truly autonomous is handling complex, multi-intent requests that have causal links.
What do you mean by that?
Well, think about a request like this. If the indoor temperature goes above 28 degrees Celsius, then turn the air conditioner on and set it to 26 degrees.
Ah, that's not just one command. It's a conditional rule, an if-then statement.
Exactly. How do you classify that? How do you create a reusable plan for a condition that might not even be triggered for hours? That shift to multi-intent classification is the next big problem to solve.
And that's definitely something to think about until our next deep dive. Okay, let's get into this. We're doing a deep dive today on what really feels like a breakthrough in vision language models. Our mission is to unpack SenseNova-MARS. That's a new multimodal agentic reasoning and search framework. We really want to understand how it's tackling these incredibly complex visual knowledge problems.
I think it's important to set the stage first.
Mm-hmm.
Your traditional VLMs, the vision language models, they've always had this problem with dynamic integration.
Right.
They'd either get, bogged down in just text-based reasoning, or they'd call a tool then another tool, but all in isolation.
A very linear, rigid process.
Exactly. It's not human-like, and it really fell apart with high-resolution images, where the answer could be some tiny, tiny detail you'd miss.
Which is where SenseNova-MARS comes in, because it tackles that integration problem head on. They built this adaptive tool suite. So it's got image search, text search, and the really crucial one, this image crop tool.
And it's all managed through reinforcement learning. That coordination is the real leap here. To see what that really means, you have to look at how it handles a complex question. There's a case study they mention. The model gets asked about the age of a racing company, just from a logo on a driver's suit.
Okay, that's a tough one. How does it even start?
Well, first, it has to use the image crop tool. It zooms right in on that logo to figure out what it is. Let's say it identifies the company as Castor.
So it isolates the key visual information first.
Precisely. Then it triggers two totally separate text search queries on its own. One for the company's founding year and another for the racer's birth year.
Ah, so it knows it needs two different pieces of external knowledge.
Exactly. And only then does it do the final math to get the answer. It's this whole chain of perception, grounding, retrieval, and then calculation.
Right.
It's how a person would do it.
And it all hinged on first recognizing that tiny logo with the crop tool. That's where the magic is.
It is. And the performance numbers back it up. We're talking state-of-the-art among open-source models. On the standard search benchmark, MARS 8B hits a score of 67.84.
But does that kind of complex approach actually translate to a real-world advantage? Or is it just, optimized for one specific test?
It definitely translates. What's so interesting is that on several search-focused benchmarks, this 8 billion parameter model, MARS 8B, actually beats some of the big proprietary models like GPT-5 and Gemini 3 Flash.
Wow. Okay, so the architecture is validated then.
It is. And to really test it, the creators made a new benchmark. It's called HRMM search.
So high resolution, I'm guessing.
Yep. It uses these massive 4K images where the tiny detail you're looking for might take up less than, say, 5% of the whole picture. It's designed to be brutal.
And how did it do?
It scored 41.64, which, on a test that hard, confirms it can do both that fine-grained visual work and connect it to the outside world.
So technically that brings up a question for me. You've got a continuous tool, cropping, mixed with discrete things like a search query. How do you stabilize the RL training for that? It seems like it would just collapse.
That was a huge hurdle. They actually had to introduce a new algorithm, a type of policy optimization, specifically to handle these diverse multi-tool paths. Essentially, it helps the agent figure out which tool deserves credit for a right answer when the tasks are so different. It's key to making the whole thing robust.
And you can see that paying off in how it behaves. The model shows this genuinely adaptive tool use.
It really does.
On standard tasks, it just uses search a lot. But throw one of those tough HRMM search images at it, and it immediately starts using the image crop tool way more. It pivots its strategy.
And it gets more efficient, too. The RL training cut down the average number of tools it needs from about 4 to just 2.
So the big picture here is that this framework pulls together external knowledge search and that really fine-grained visual analysis.
Yes. It's a huge step closer to how people solve these kinds of visual puzzles.
But the sources are also pretty clear about the limitations. Even with a perfect tool call, the model can get tripped up by what they call retrieval noise.
Right, like confusing based in with born in from a search result, or just not quite linking the thing it sees to the right search term.
Which leaves you with a really interesting final thought, doesn't it? We're getting really good at teaching the models how to use the tools. So is the next big bottleneck not about invoking the tool, but about teaching the model how to interpret and synthesize the messy, noisy, often contradictory information it gets back from the real world? Something to think about. Okay, so for today's deep dive, we're jumping into something that feels like it's straight out of science fiction. We're talking about virtual avatars that can actually hold a conversation with you, not just, passive talking heads. And we're going to unpack this new framework called avatar forcing, which is really trying to solve the two biggest things that kill the whole experience.
Right, the lag and that kind of creepy emotional stiffness.
Exactly.
I mean, that stiffness is really the core of the problem.
Yeah.
A real conversation is, it's bidirectional. You nod when I'm talking. I smile when you see something interesting. But the older models were all one way. They were just focused on lip syncing at you.
And if they did try to react, the delay was just awful.
Totally. It was like talking to someone on a really bad satellite link. It just kills the immersion.
Lag is the ultimate relationship killer. So let's start there. How did they actually get this thing to be real time? I mean, it's taking in your voice and your movements all at once.
Well, the big breakthrough is in how they generate the motion. It's what they call a causal solution. The old way, the baseline system, it had to wait for future context.
Wait, what does that mean? It had to hear your whole sentence before it could react.
Essentially, yes. And that led to a latency of about 3.4 seconds.
3.5 seconds, that's not a conversation.
It's unusable.
Right.
That's an eternity.
Precisely. So avatar forcing just crushes that. It gets the latency down to around 500 milliseconds.
Half a second. So that's almost a 7-time speed up?
It's a 6.8 times speed up. Yeah, a massive jump. And they do it by generating motion based only on what's happening right now. Plus, they efficiently reuse past information with something called KV caching. Basically, it stops the model from doing the same work over and over again.
Okay, but half a second, 500 milliseconds. Is that actually fast enough to feel real time, or is it just a technical achievement?
It feels real time enough in the flow of a conversation. Because the reaction is immediate and causal, it's that jump from 3.4 seconds that makes all the difference. Got it. So they've solved the delay. But you can still have a really fast, emotionally dead avatar. Which brings us to the next wall.
The expressiveness problem.
Right. We've all seen them, the digital heads that just sort of stare and blink. How do you teach an avatar to give like an empathetic nod or a genuine smile, especially when the training data for that stuff is so stiff?
This is where they got really innovative. They used a method called direct preference optimization, or DPO.
Okay, DPO. So instead of just feeding it millions of good examples.
Exactly. They engineered what they call less preferred samples. They basically taught it what a bad interaction looks like.
So they created synthetic losing examples.
That's a perfect way to put it. They'd intentionally drop the user's signals, their motion, their audio cues, and then teach the model that generating a reaction with those signals is better than generating one without them.
So it learns through contrast. It learns that reacting is better than not reacting.
And it does that without needing any expensive human annotations. It's a really clever shortcut.
And the results speak for themselves, right? In the human evaluations, this new model was preferred over 80% of the time.
Over 80%, yeah. People found it way more natural, more responsive. It would actually smile back when the user smiled, which the baseline just couldn't do.
That's huge.
And they proved it, too. They ran this ablation study.
A controlled experiment.
Right. And when they removed the user's motion signal, so the avatar could only hear the user but not see them.
What happened?
It just became a statue. As soon as the user stopped talking, the avatar went completely still. It proves the avatar needs to literally see you smile to smile back.
Wow. So let's bring this all together for our listeners. The two big takeaways here are, one, it's incredibly fast, so it feels real.
Low latency. Yeah.
And two, It's genuinely expressive. It gives you these reciprocal social cues that make it feel like you're talking to, well, something that's actually listening.
It's a fundamental shift. And if you think about the big picture, this opens up so many doors for things like, virtual chat or more immersive education.
Yeah.
But the creators are also very clear about the potential risks.
Yeah.
Things like deep fakes or identity spoofing become a bigger concern with technology this realistic.
Absolutely, something we always have to keep in mind. Now, the source paper mentions this is all focused on head motion and facial expressions. It doesn't really model things like hand gestures yet. So we want to leave you with a final thought. What other nonverbal cues beyond the face do you think a perfect interactive avatar would need to finally convince you that it was real?